Welcome to this last lecture of the EANA Spring School on hydrothermal vents. My name is Ruth Sophie Taubner and I'm the host of this very last session. And you know, the one spamming you with emails and messages in the chat box. Before starting with this lecture, I'd like to take the opportunity to thank the EANA President Barbara Cavallazzi for being so passionate in organizing this Spring School. She's the main force behind the EANA 20th anniversary events, and without her motivation, this Spring School would never have happened. So thank you a lot, Barbara. Coming back to the following lecture, I'm very happy to welcome Dr. Steve Vance from the Jet Propulsion Laboratory, Caltech in the US. Steve is an astrobiologist and geophysics studying the workings of icy ocean worlds. He obtained his PhD in geophysics and astrobiology from the University of Washington in Seattle. After that, he came to JPL as a NASA postdoctoral fellow and became a staff scientist in 2010. He's currently supervisor in the Planetary Interiors and Geophysics group. Steve studies the interiors of icy bodies like Jupiter's moon Europa, dealing with questions about ocean composition, dynamics, habitability through simulations of icy world ocean chemistry in the laboratory, coupled with theoretical models of fluid circulation in deep oceans. So Steve, thank you for joining us today. I'm really looking forward to your talk. There will be, for your information, there will be a break in between, and after Steve's talk, he will be happy to answer your questions posted in the chat box. So it's my pleasure to hand over the virtual microphone to you, Steve, and the stage is yours.
Thank you for the very nice introduction and also for the invitation and the chance to be here. So in this talk today, I'll try to focus on this theme of hydrothermal systems in ocean worlds, and my perspective will, of course, come largely from my own work, but I'll try to give a feel for what's happened in the field in the last 20 years or so in general. And after the break, I'll provide a walkthrough of NASA's Europa Clipper mission, which is planned in the next 10 years to explore Europa and investigate its habitability. So let's start in with some big picture ideas. You know, hydrothermal activity is an intriguing possibility at Europa and a part of what we think makes Europa habitable. But just as Earth is a complex system, which you know has textbooks devoted to studying the complex interplays between biology and geology that comprise the Earth system, we can think of ocean world science, or in the focus on Europa, we can think of Europa system science. We don't know if biogeochemical cycles are activate Europa, but just thinking about the physical or geochemical processes, if you will, I think taking a global perspective is necessary to understand the energy that might be available for life, the materials that might be available, and where they combine in ways that might be most supportive of creating habitats. So thinking about the Earth system is helpful and is really our as is often said in astrobiology, Earth is our only example of a thriving biosphere. It's the only place where we know of life. So let's think about the Earth system in a Europa sort of way. So cross section of the habitable region on Earth. A reminder that habitable region is only a few kilometers thick, and it's characterized by this global ocean with a depth on average that's roughly about 4 kilometers. Of course, near the coastlines, it's much shallower, and only in a few places is it much deeper than that. In the deepest places, the conditions are, I'll just point out, are comparable to what we might find at the bottom of Europa's ocean. And I include this scale here that is the radius of Europa, just to be clear. But so the ocean is a major characteristic of Earth, but that ocean is in direct contact with an atmosphere that's rich in oxygen, and that oxygen is generated largely by photosynthesis, of course. And so the role of the sun is really important for generating oxidants that make multicellular life possible. Now, we also, in the last 50 years, have come to understand that the seafloor also hosts really interesting and diverse ecologies. in a variety of different types of hydrothermal systems. And let me just move this video so I can see my presentation. Pardon me. Okay, so yeah, so the hydrothermal systems, it's worth emphasizing, often support organisms that subsist solely on chemical energy from Earth's interior. So that's mainly derived from radioactive decay of materials in Earth's interior, uranium, thorium, and potassium, and the release of heat and the consequent alteration of minerals at the seafloor generates reductants that, when combined with seawater, create a redox gradient that life takes advantage of. So in some sense, the presence of oxygen is in the ocean is important for supporting that life. So many of today's hydrothermal ecologies do benefit from photosynthesis, but we know there are organisms that also can subsist in the absence of that oxygen as well. The important thing is developing these redox gradients. So another thing to point out is the characteristic depth of water-rock interaction. Let's say it's nominally 6 kilometers. This is from some work that was done a number of years ago, and that's a bulk number. But bulk numbers are appropriate if we're thinking about a place like Europa, where we don't know much about the details of the what's happening in the interior. We can think only on a global scale currently. Oops. Yeah, so the Earth system has all kinds of, by contrast, has all kinds of different features that result from its topography and from details of how the mantle is overturning. Namely, plate tectonics serves to take carbon out of the atmosphere, carbon that's deposited on the seafloor through weathering, and also by the deposition of waste from organisms in the ocean. And yeah, just emphasizing again the role of the sun in all of these processes. So we can ask, what are the different feedback systems in Europa and other ocean worlds for that matter? And I want to emphasize this other point, that the habitability of Earth has changed through time. We can see that the evolution of life, the different types of organisms that have been present throughout Earth's history, here portrayed from 4.5 billion years ago when the Earth formed to the present, in terms of the abundance of oxygen in the atmosphere at its current level of 20%, from 0 at the beginning, when nevertheless life was present. And you see there are periods when oxygen was quite high and in an intermediate range. And so it's an important reminder that when we think of the habitability of a world, we have to ask what are the process, how the habitability might have changed through time. It's interesting to think about how changing habitability might also be a driver for evolution. Okay, so focusing in on Europa-like conditions a little more, and borrowing from a figure from a paper by this school's first speaker, I believe Mike went first. There are hypotheses about life's origin in low-temperature hydrothermal systems that involve the detailed chemical interactions of water percolating through the seafloor, and those don't necessarily involve the influence of the atmosphere and the sun. So we can think of taking that away, and we can think of changing the characteristic depth of the ocean to the depth of Europa's ocean of nominally 100 kilometers. And so maybe if we can figure out the type of hydrothermal systems, if any, that might be present in Europa, we can envision an independent origin of life there. And even in the absence of such an independent origin, with the idea that life was seeded throughout, we can imagine ecosystems in hydrothermal environments on Europa. So I'll talk a little bit about what those systems might be, but first I want to talk about the oxidant couple, the replacement of the atmosphere. And so we can think in some ways of, this question mark is a little bit important. So this characteristic depth of interaction, we'll return to that in a bit. because it factors into how much energy might be available for life in Europa. So we can think of Europa's ice in some sense as filling the role of Earth's atmosphere. And the way that happens, and Mark might have covered this a little bit, but I think repetition is helpful. The way that happens is through the creation of oxidants at the surface. So Europa is somewhat unique among ocean worlds for having a high incidence of charged particles at the surface that break up water. And because the gravity is pretty low on Europa, the hydrogen preferentially escapes. And so what's left behind are molecular oxygen, hydrogen peroxide, potentially also perchlorates. These oxidants also combine with sulfur deposited at Europa's surface, sulfur deposited from volcanic neighbor Io, that then creates a sulfur cycle at the surface that also generates sulfates, SO2, and all kinds of oxidized materials that potentially make their way through the ice because of the high level of geological activity at Europa's ice, thus creating a flux of oxidants into the ocean. And so just to tie that all together, then, the flux of reductants from the seafloor is potentially an important complementary couple to oxidants from above. And the resulting consequence of that is that there could be a large amount of chemical energy available for life in Europa. So here's the cross-section for Europa, a reminder of the nominal scale of the ocean. And we can ask, what is the depth of percolation of fluids into the seafloor? Here I've depicted the possibility that hydrothermal vents move their material directly to the ice. This has been hypothesized to occur if hydrothermal systems are present at high latitudes. This is due to the rotation of Europa. There's a phenomenon in fluid dynamics of the formation of so-called Taylor columns, in which the rotation ends up confining a rising plume into a column of some characteristic width of, in Europa's case, something like 50 kilometers. And so there's some potential that if materials are coming out of the seafloor, they may get entrained into the ice somewhat directly from below. And so maybe we have some chance of sampling those materials. But we at this point, we don't even know the composition of Europa's ocean. In contrast, Earth's ocean has a dominant composition of sodium chloride. There's various research that's been published about the possibility of magnesium sulfate that that matches magnesium sulfate seen at Europa's surface, and so might be an explanation for the ocean's composition. Sodium chloride is come into a little more favor lately, and we can talk about that in the discussion. But so just to highlight that we don't know the composition of the ocean at this point. It's just a little more detail about that radiolytic processing that I mentioned. It's just in the upper few microns that happens for the most part, although some secondary scattering of high energy particles will deposit energy more directly, and high energy electrons can penetrate to some more significant depth. And so the movement of that material into the deeper ice requires some additional churning from micrometeorites and geological processing. So that geological processing in recent years has become a little more nuanced. People have looked at Europa's surface and found potential evidence of subduction-like processes in the ice, places where some of the linear features seem to show that an ice plate has moved under another ice plate. And this has been referred to as subsumption, because there's no evidence that the plate makes its way all the way through the ice. And what happens in plate tectonics on Earth when that occurs is that you end up having some uplift on the other side due to the underplating of the subducting slab. Instead, at Europa, the subducting slab, it seems, gets entrained and thermally equilibrates with the ice before it can make its way all the way down. An interesting consequence of this, however, is that putatively the impurities in the ice end up melting and might explain the pockmarked features opposite the linear features that are observed on Europa. So we can look at a picture of this. Here's the famous Thera and Thrace macula on Europa. Thera, at least, being hypothesized based on the limited topographic evidence from the Galileo mission to be a region where the ice has collapsed entirely. That is, the localized material is lower than the surrounding terrains, which might be explained by melting underneath that led to the formation of the chaos. And in this region, it seems that the chaos might have been breaking off at the time that Galileo was there, or at least in the recent past. If that occurs, the presence of brines might imply that the brines at some point, instead of freezing in place, percolate through the ice. And this paper and some subsequent work have pointed out that percolation would happen on a time scale of 10,000 years, which is short compared to the age of Europa's ice. So thinking a little bit about the flux of oxidants to the ocean, this is from a paper by Hand et al. From 2007. Sorry, the text is cut off there. And they looked at the geological age of Europa's ice, and which is at the time was firmly in the range of 30 to 70 million years. I think that range might be as old as 200 million years, or even a little bit more. But in any case, depending on how long it takes for materials to be delivered to Europa's ocean, you can come up, and based on estimates of the generation of oxidants at the surface, you can come up with an estimate of the flux of oxygen, hydrogen peroxide, and other materials into Europa's ocean. So they also, in that paper, made an estimate of the moles of reductants generated at the seafloor. In their case, they focused entirely on high temperature hydrothermal activity, so-called black smokers, for which there were some inventories of the flux of reductants on Earth. And so by looking at Europa's heat flow, you can get an estimate of the total fluid circulation through the seafloor and come up with a number for the number of moles per year generated. And that number was about 10 to the 9th, which conveniently is matched with the oxidant fluxes. So that begins to look like a nice redox couple at Europa, where you might have oxidants balanced by reductants. Now there's some error bars on all of this, of course, and so you might envision the reductants being a stronger flux than the oxidants, which in that case we might imagine a reducing ocean, in which case the region just under the ice might be where the oxidants are taken up by any biology that might be present. So to elaborate on that work by Hand et al., these are the estimates they made based on Elderfield and Schultz, which perhaps you've encountered in some of your work. These were the abundances in millimole, and they might have used molar, but they're roughly the same. And so the consequent fluxes are shown here. And so the circulation was from Elderfield and Schultz, and the abundances were from this paper by McCollum, which is a nice bridge between, McCollum did some nice work bridging hydrothermal chemistry on Earth with possible chemistry on Europa. And so we can come up with a representation for our own representation for the hydrothermal flux on Europa. I did this based on a paper from GRL, and this will show up later in what I'm about to show you about the possible alternative for a mechanism for hydrothermal flux in Europa. So in this example where you have a high flux of oxidants, supposing that you don't have a whole lot of hydrothermal activity at Europa's seafloor, and that has been supposed because in contrast with Io pictured here, which is highly volcanically active, here's a picture of a volcano spewing into space. In contrast, it's been supposed that the majority of tidal heating in Europa might instead happen in the ice, and because the ice is less viscous and might be optimally poised to take up that tidal flexing. In such a case, it's been supposed that the seafloor is entirely dead and devoid of hydrothermal activity. And if that were the case, then some previous researchers suggested that the ocean might march inexorably toward a really low pH state, comparable to the pH of battery acid, within a couple billion years after Europa's formation. So that's an interesting possible consequence, something that seems like an extreme case that we might explore using the Europa Clipper measurements that I'll describe later. I tend to think that hydrothermal activity will be happening even in the case where tidal heating of the seafloor is at a minimum. So let me talk about that minimum case a little bit. So here's how we might get a reducing mantle in Europa without vigorous convection and without volcanism at the seafloor. So a number of years ago, I adopted an estimate for the depth of fluid percolation in Earth using the same physics to estimate the depth of fluid percolation on Mars, on Europa, and then many other moons. So we'll focus on Europa, but I'll show some results for other moons as well. And so that mechanism is based on the idea that if you have a, supposing the mantle was made mainly of olivine, of some characteristic grain size, let's say 1 millimeter, we can look at the influence of thermal expansion and anisotropy. So here's those characteristic grains in a nice matrix, but some of those grains are not going to have the same thermal expansion properties as the surrounding grains. So as a result, as the Europa cools naturally, either due to the decay of tidal heating or due to the natural cooling as radiogenic materials decay, as happens in all planets, then that should generate fractures. And so the way that's done is, the extent or the efficiency of fracturing is quantified in this model that we adapted. This figure is from a subsequent paper by Neveu et al., who also adapted the same method, so demonstrated that they got the same numbers that we did. And they also looked at other processes, drying and hydration of materials, dissolution and precipitation of materials along flow paths, and also pore fluid expansion. They found that this effect, the thermal expansion and anisotropy, was the most important one. And so if we have a depth of fluid circulation, then we can, and if you want, sorry, I just want to say that I'm going to skip the math on how that works, but we can talk about it later if you want to see it. And instead, I'm just going to say there is a model, and we can estimate the depth of circulation. For Europa, we get a depth of about 25 kilometers in the present day. But importantly, also because Europa continues to cool, this fracture front is moving downward through time at some rate it's pretty small. It's like microns per year, but one can compare it to the global extent of seafloor spreading on Earth, which is also a mechanism for generating fresh materials. And those fresh materials are important because the low temperature alteration of those materials through serpentinization, namely the hydroxylation of phthalate, ferrocylite, and forsterite, which I believe Mike Russell should have gone through in some detail, it's an exothermic reaction generating some heat, but more importantly, for the iron-bearing elements, it generates hydrogen. And so there's a flux of hydrogen that we can quantify in some rough way that's independent of the extent of melting in the interior. Is there a question? Okay, I'll continue. If there are questions, I'm fine taking them. So this kind of quantification of fluxes of hydrogen has been done for Earth, for the Earth system. So this is a nice paper by Sherwood Lawler et al. From 2014, looking at deep mines on Earth and looking at the fluxes of hydrogen. And so they put together their estimates with some previous work and came up with the global flux for the Earth system, which I'll summarize in a second. So we can do the same thing for Europa. We can do it for many worlds. So it simply requires that we use our fracturing model. Here's that 1 millimeter grain size that I mentioned. I throw this figure up here. This is from our recent paper talking about how this process might play out through time, because I think it nicely summarizes how this process might work on different worlds, and that the pressure and temperature profiles in different worlds are a common feature that we can think about. So each of these curves starts at the putative seafloor for a two-layer model comprising a hydrosphere and an underlying rocky layer. And so all these models are consistent with the known densities for these worlds. The lighter colored kind of purple lines here are worlds where the constraints aren't as good. And so the other colors are just notional colors corresponding to the worlds, Mars and Europa and Earth, that make them easier to see. I can point out that this fracturing model doesn't work for the larger worlds because the pressures are so high at the rock interface that fractures would close off. And so in a place like Titan, where clearly many volumes of hydrocarbons have been produced, if any of those were produced endogenously, there must have been some other mechanism for the rock to be exposed to water. We can talk about that as well if people are interested in it. But as I mentioned, this process plays out as a function of time, and so we can get a present day abundance or flux rather of oxidants and reductants. The oxidants coming from the estimates that I showed you earlier. Let me put all that together, and I can give you an estimate of the case in which no tidal heating happens in Europa's seafloor. That's over here. That's the serpentinization case, and I can put that together with the other estimates for the cases where tidal heating does go into Europa's seafloor. So this is roughly the range of possible tidal heating in Europa's seafloor. And the more tidal heating in the seafloor, we can think that the more tidal heating in general, rather, the thinner the ice is going to be. Whereas if the tidal heating is lessened, then the ice is thicker. So just wanted to point that out. So here's Earth's net oxygen. That's the reference for that is contained in this paper here. So you can think of roughly 2 times 10 to the 13th moles per year. And here's the range for Earth's net H2. Notice that it's a pretty broad range. This is from that paper that I showed you earlier by Sherwood-Lawler et al. It's offset by about an order of magnitude. And here's the range of flux for Europa's ocean. Now, this is a pretty broad range. This is based not only on the estimates of Hand et al., which are in this lower region. Here's that 10 to the 9th that I showed you earlier. But the other work by Greenberg and Pasek suppose that the delivery mechanism might be even more efficient. And so that's where this upper bound comes from. So we can just take into account a very broad range. And I should mention that range can be even lower than this, of course, if overturning in the ice is not really efficient. So let's look at the high temperature flux of hydrogen due to hydrothermal activity. So as I mentioned, we don't know the amount of hydrothermal activity in Europa's mantle. And also the hydrogen fluxes are estimated as a function of the circulation through the seafloor, which is a function of the heat flux from Europa. So as the heat flux decreases, the circulation decreases, which means the hydrogen flux also decreases. So that's how that's quantified. So it trends downward by a little less than a factor of 10 for this range. And I suppose that once the ice becomes sufficiently thicker than 10 kilometers, then solid state convection turns on. And in that case, let's just assume for now that high temperature hydrothermal activity then turns off entirely. I mentioned before that's been a prevailing thought about how Europa might work. So conveniently, this is not cooking the numbers too much. We didn't try to come up with this outcome, but it turns out that our 1 millimeter grains lead to this. And I believe the error bars here are for considering larger and smaller grains respectively. It changes the depth of the fracturing front. But what happens is that as the seafloor cools, the depth of percolation increases, and also the rate of percolation into the seafloor increases, which means that the estimated hydrogen flux from serpentinization also increases. And it just happens that in this very low end case, the flux of hydrothermal hydrogen from serpentinization is comparable to the upper end flux of hydrothermal circulation in the high temperature case. So in both cases, though, the amount of hydrogen is roughly in that 10 to the 9th, 10 to the 10th range that I showed you earlier from Hand et al. And depending on what the oxidant flux is, whether it's the lower bound that I mentioned or that upper bound, you either have a situation that's like the Europa case that I mentioned earlier, where the oxidants and reductants are matched, or in this more optimistic extreme, you have a case where the oxidants are, in Europa's case, also an order of magnitude higher than the reductants. So what that means for possible life on Europa, I'm not sure, but the possibility of determining what's happening at Europa in the future is really intriguing, and it's nice to have a framework to think about in terms of the different types of activities that might be occurring and their consequences for the ocean's composition. So let's see, I'm going to talk for another few minutes, and then we'll take a break. So I want to then roll this all up into thinking about Europa's system science, namely, how did the ocean form, and how did volatiles evolve through time? So some recent work that I've been involved in. This was a former postdoc working with us, is now an employee at JPL, Mohit Melwani Daswani. Had this nice paper. It's in revision, so recently resubmitted. But the idea there is we can think of Europa's ocean evolving from subsequently to its formation from the global alteration of materials. So the idea is that we have pretty good evidence that Europa has a metallic core, which means that the temperature in Europa's interior had to get at least up to the temperature of the iron sulfide eutectic. And so we can construct detailed models of Europa's interior using modern frameworks for equilibrium petrology. And then we can look at the volatile fluxes that would come out of those materials. If we assume that Europa formed from meteorites that would have been present in the region of Jupiter when Europa formed. So the same materials that made Jupiter minus the hydrogen. So this is a self-consistent model for present-day Europa. And here's our earlier model when the ice was much thinner, possibly absent for brief periods. And so we can ask how the volatiles outputs into the ocean change through time. So I have some details that I can get into on that. I'll just briefly flash this figure from the paper, which shows at a pressure of 3 GPa, or about 700 kilometers below Europa's surface, for the different meteoritic models that we assume. These are the 3 nominal models. Very carbon-rich chondrite, which is a primordial meteorite, or a slightly less carbon-rich so-called CM chondrite, or some mix thereof. You can see that the prevalent mineralogy firstly varies as a function of temperature, but it's very different for the different minerals, for the different input materials. So that's going to affect the extent of volatile output and the consequent composition of the ocean. So earlier work had looked at how Europa's internal heating might have changed through time. I can emphasize both in this work, this recently resubmitted work, and also in our earlier 2016 paper, we pointed out that in order to have serpentinization, even if volcanism is absent in the present day, it would have had to have occurred at some earlier time. You start from a condition of assuming that the minerals are anhydrous, and so then are primed for retrogressive metamorphism, that is, alteration due to cooling. And so one way to have that happen is due to a pulse of heating as Europa's eccentricity changed through time. So this is a model by Hussmann et al. It's a theoretical model which propagates the Laplace resonance, this kind of hypnotizing orbital resonance that's the moons are currently engaged in which for every one orbit of Europa, Io orbits twice, and likewise same resonance for Ganymede and Europa. So that resonance would have changed through time, and the result is the eccentricity of the moons also changes through time. And that part of the reason for that change is that the response of the interiors of these moons to tidal flexing changes through time because of their changing internal heat. You can imagine they were squishier earlier in history when they were warmer. And so perhaps they reached some resonance in which they were optimally dissipative. And so for Europa, that would have meant that the temperature in the interior would have gotten indeed high enough to melt that iron sulfide mixture. And then it might have undergone a subsequent pulse. So it could have cooled rapidly after that and then undergone a subsequent pulse. So one can imagine a rapid or a period of a few 100 million years in which serpentinization occurred, and then in which volcanism returned. And one could imagine then having some kind of alteration after that. So this begins to look like the kind of overturning that happens in Earth's mantle. So we can at least ask what that might have looked like on Europa. And so in our earlier paper, we portrayed how hydrogen production would have changed through time due to the progressive radiogenic cooling. So this is without consideration of tidal heating or changes of heating through time. So you can see there's this progressive decrease in the flux of hydrocarbons, of hydrogen. And I'll just note that for Enceladus, we have a flat line here because Enceladus is so small, it's predicted that the interior would have always been fractured. And that's to some extent consistent with inferences of Enceladus's internal density from the Cassini mission, which seemed to require that Enceladus rather has a very porous interior. But we can overprint that. So here are our estimates that I showed you earlier for the current range of hydrogen fluxes for Earth, and here are those same oxidant fluxes I showed you earlier. So just emphasizing this all matches up with what I showed you earlier. But we can overprint that pulse of heat that I showed you earlier from that Hussmann work, and we can imagine that perhaps there was some post-resonance output of hydrogen. This is the result if you just estimate what is the hydrogen flux. If you just serpentinize all of the 25 kilometers or so of rock in Europa subsequent to that pulse over a short period of time. Now that's it's sort of a back of the envelope estimate, but it's an interesting idea that you might have had these somewhat perhaps catastrophic fluxes of materials after these periods. And we can look at the corresponding heat from serpentinization and radiogenic heat and compare that with the tides. So that's all really interesting stuff. I think again, it's a framework in which to think about how Europe might have changed through time. I'll just, as I'm winding down this part of my talk, I'll mention some exciting work that just came out that was led by Marie Bankova and co-workers mainly in Prague and Nantes. Mohit and I had some small role in this work of helping to connect their work looking at the tidal heating in Europa with the corresponding fluxes of reductants. What I want to highlight from this work here in this figure from the paper is that they looked in detail at the tidal heating in Europa due to changing eccentricity. So similar to what I showed you from Hussmann et al., albeit with much more high fidelity models, spatially speaking. And they looked at different chondritic inputs, and so they took into account the possibility that you had more or less radiogenic materials. There's some more details about this that I've covered over, but just to give you some idea, they also come up with changing amounts of tidal heating over Europa's history, and that's compared with the overall radiogenic heating, which you can see was larger than the tidal heating for most of Europa's history. And in the more recent period shown here, you can see that there's some vast changes in the melt rate, and that melt would persist to the present day. So this new work is suggesting that perhaps high temperature hydrothermal activity may actually be occurring in the present day on Europa. And so I didn't include it in the talk here, but the result of this is that they suggest that tidal heating, rather volcanic melting from tidal heating may be occurring in the present day. And if so, it's probably most likely focused toward the higher latitudes near the poles, which perhaps is convenient in terms of connecting with providing direct flux of materials from the seafloor to the ice if hydrothermals are present and the flux of materials is confined in these Taylor columns that I described earlier. So I'll just end this part of the talk by connecting this with some models for Europa's ocean composition. So this is, from an abstract from Zolotov et al. I'm gonna pause this. And they point out that if you do an equilibrium chemistry model for Europa, looking at the assemblage of ions in the ocean, so here on a log scale showing the moles of different ions per kilogram of water as a function of hydrogen fugacity or equivalently of the pH of the ocean. You can see that perhaps in a reduced ocean, which might have been earlier Europa, might even be today's Europa, you can see that sodium and chlorine are the dominant species at a little less than 1 mol, whereas the less abundant magnesium and sulfate become dominant when the pH gets sufficiently low. And so you see that magnesium and sulfate are plausibly end members for the ocean. And so we can consider for different models of the ocean what different properties might be, like here the electrical conductivity of the ocean. And so in recent work, we've looked at that to consider whether those differences in properties might provide geophysical clues that we can use to look at the consequences of hydrothermal activity through time. Yeah, so I'm happy to share some details and an overview of NASA's Europa Clipper mission. I'm a member of the science team on Europa Clipper. I've been involved with that for some time. So the Galilean satellites of Jupiter, people might be familiar with this. This is a sketch that was drawn by Galileo more than 400 years ago now upon viewing the satellites for the first time through his telescope. And so we can contrast this with our current knowledge of Jupiter and its companion moons. This information brought to us thanks to the Voyager missions, but really the fidelity of these images brought to us by the Galileo spacecraft, which conducted its investigation of the Jupiter system for 8 years, starting in 1995. And so here the moons are shown with their relative distance from Jupiter, not to scale, of course. And you can see there's a progression in their size and in their level of alteration, with Callisto being the oldest, as indicated by the high abundance of craters. Io being the geologically youngest, with its active volcanic surface, with more active volcanoes than Earth has. And so, but we're primarily interested in Europa because, as we've been discussing, there's good evidence for an ocean directly in contact with rock, and so let's think about the themes of things that we can explore for Europa. And I hope, to some extent, this discussion will investigate one of the questions that I saw. Well, we'll elaborate on one of the questions that I saw, which was mechanisms for getting sulfate, and I assume also other oxidants, into Europa's ocean. So as I mentioned earlier, the surface of Europa is geologically very active. We know of only a few craters. Here's one of the main ones, Puil, shown here, and here in a zoomed in, higher resolution, false color image. But generally, Europa's surface is crisscrossed with plains, these ridged plains that bear the marks of fractures that have occurred over the last 100 million years. So you have layers of fractures that have been covered by other fractures, and you have places where the fractures have been offset from each other, suggesting tectonism. And then, as I also mentioned, we have regions where the ice is broken up entirely, and you can still see the fractures that were present, some of which then cut through the chaos. And zooming out from that, we have associated features, so-called lenticulae, that are perhaps associated with subduction underneath the linear features seen here. But in general look like smaller versions of chaos. And the discoloration of these features varies depending on where you look, which may have something to do with the age of the features. It's really not clear. But the reddish materials in general they're spectroscopically in the infrared spectrum, they're non-icy materials, and they've been associated with, linked with different types of salts, and so the occurrence of these reddish materials with the linear features has been interpreted to mean that these are oceanic materials coming up from underneath Europa. In an extreme case, potentially they're ocean materials coming directly from the ocean, which would be possible if the ice were very thin. Geologically, it seems that based on the interpretation of Europa's surface, that the ice could be as thin as 3 kilometers. The community seems to be in favor of interpretations that are much thicker than that, perhaps 10 kilometers. But we're really not there in terms of knowing for certain just yet. So we have some constraints on Europa's interior properties. This is from gravity science measurements by the Galileo spacecraft. Basically, the Doppler shift of the radio signals that were beamed continuously to Earth during the Galileo flybys of Europa, which indicate to us that there is most likely a rocky interior under a much lower density ice layer, hydrosphere, and most likely also a metallic iron core. There's only a narrow window of possible solutions to the gravity data that allow Europa to not have an iron core. So this information doesn't tell us directly that there's an ocean, nor does it tell us at all whether there's currently hydrothermal activity as depicted in this picture. But based on the density of Europa and its density structure as inferred from gravity, we can confidently say that Europa has about twice the H2O of all the water on Earth's surface. How much of that is liquid is not entirely clear, but the fact that some of it is liquid is pretty well established due to the magnetic induction features that were seen by the Galileo magnetic investigation. So this animation is depicting how that magnetic induction works. So importantly, Jupiter has this tilted magnetic field, tilted by about 10 degrees. So you can see that the North Pole is pointing in a different direction over time. So, and that direction changes with Jupiter's rotation rate of 10 hours as seen from Europa. So during the course of Europa's 85-hour orbit, it sees the direction of the field change about 8 times. And so what that means is that any conductors in Europa see a changing direction of field, which then changing magnetic fields can induce currents in the fluid that then generate response fields. So this animation is showing the responding changing magnetic field within Europa. And so the best explanation for that induced signature is a near surface conductor, which most likely is charged particles dissolved in water, so ions of water, aka a salty ocean. Now, we think, based on our understanding of Io, that Europa also experienced extreme heating. So just to explain what I mean by tidal heating, Europa's orbit is eccentric. That is, it's not quite circular. And so Europa will experience a changing gradient of gravity from its Jupiter-facing and anti-Jupiter-facing sides, which leads to a changing shape of Europa, shown here in exaggerated form from Europa's perspective. And that changing shape means that in the more viscous, the less viscous materials that can flow, that means you generate heat and potentially you generate melts. And so this picture is showing reddish regions within the ice corresponding to heating, possibly heating all the way up to the melting temperature, and similarly reddish materials indicating heating in the rocky interior, also possibly generating melt. And so, of course, that brings the potential for hydrothermal activity. I think some music's going to play when I push this, but I'll just play this video. So the possibility of black smoker hydrothermal systems at Europa is clearly of interest when thinking about possibility of life in Europa, for the possibility of not only having plenty of water, but also essential elements and chemical energy, possibly to support ecosystems like the ones seen here that are subsisting entirely on chemical energy. So the Europa Clipper mission then is conceived with the overall goal. So now I'm going to adopt some sort of formal language to describe the mission. So the overall goal agreed upon with NASA is to explore Europa to investigate its habitability. So in service of that goal, the objectives of the mission are established to investigate the ice shell and ocean of Europa. So to understand the thickness of the ocean and its composition, and also the thickness of the ice shell and its geology and its whether it's geophysical processes, whether it's overturning, and whether there's any melt within the ice. Along with that, we have the potential to understand Europa's composition based on its surface properties, and thereby to also, in combination with our understanding of the ice shell, to understand what it tells us about the composition of the ocean. So a rigorous study of Europa's geology, its rich geology that I described earlier, will allow us to put all those things together to understand what's happening in Europa. And recent evidence, mainly from Hubble observations conducted almost 10 years ago now, as shown here, suggests that Europa might also be active in the present day. And so we're keenly interested in the possibility of plume-like activity related to the plumes observed at Enceladus, but almost certainly not by the same physical mechanisms as what happens at Enceladus. And lastly, a part of the Europa Clipper investigation will be to look at Europa at the highest possible resolution. Here's some, I think, 8 meter per pixel imagery, some of the highest resolution imagery from the Galileo spacecraft, showing Europa's modeled surface, non-icy materials, many of which look like lag deposits that have settled in the lowest regions, bisected fracture features, reconnaissance, not only to understand the most scientifically interesting sites on Europa, but also possibly the safest landing sites. So that's a feed forward for a potential landed mission on Europa. So to meet all of these objectives and meet the overall goal of Europa, NASA selected a number of instruments, a suite of instruments, very capable instruments, sort of next generation instruments to investigate Europa. So here, those instruments are grouped by in situ, shown in yellow, and remote sensing instrument, shown in blue. So I'll go through these instruments in very rough terms. The in situ suite consists of a mass spectrometer to intercept particles in Europa's atmosphere, the volatile gaseous particles. And as a complement to that, the Europa Clipper also has a dust analyzer, the SUDA instrument, that can look at solid particles, perhaps from plumes, but also particles ejected from Europa's surface by micrometeorite impacts, so-called sputtering. Radiation can also do this. And so that's comparable to the INMS and CDA instruments that were on the Cassini spacecraft, but with much higher spectrographic resolution and also much higher sensitivity, spectrometric resolution, I should say. And also, the in situ instruments consist of a plasma and magnetic field suite, namely the Europa Clipper magnetometer and the PIMS Faraday cups, which together can detangle the induced field of Europa from the external fields and from the ionosphere and plasma effects in Europa's environment. And so to map Europa in multiple wavelengths, from the UV out to the mid-infrared, Europa Clipper has the Europa UVS instrument, the Europa Imaging Suite, consisting of a narrow angle and wide angle camera, and the eThemis imager, and also the MISE instrument, which is a mid-infrared spectrometer going from about 1 to 5 microns. and the reason instrument, which is a ice penetrating radar sounding at 9 and 60 megahertz to look at the deep properties of the ice all the way to the ice-ocean interface, but also the near surface structure of the ice to help with the geological investigation of Europa. So altogether, these instruments should allow us to understand Europa's composition and the churning of its ice, including the deposition and generation of oxidants at the surface, possible liquids within the ice, and transport of materials through the ice into the ocean, potentially vice versa. So the way that Europa Clipper will conduct the investigation will not be by orbiting Europa, but rather by orbiting Jupiter and flying by Europa many times, more than 40 times. So here is depicted a global web of flybys. So each of these lines is a flyby of Europa, and the colors indicate the approach to Europa, with the closest approach for some of these in red being as close as 25 kilometers. And so you can see that through this series of flybys, we'll build up global imaging of Europa in its subjovian and antijovian sides. So this is the subjovian, the antijovian side pointing away from Jupiter, and this is the subjovian, the side pointing toward Jupiter. And so on the right, not shown in great detail, but just showing you that we develop, for all of our trajectories, we develop these maps that show us what the footprint will be of the instrument to show what kind of coverage we get. You can see that for the compositional instruments and thermal instrument, we get global coverage of Europa in many regions at very high resolution, depicted with these different colors. So I don't want to get into all of the details on that, but I'll mention that the highest resolution imaging of Europa will be at less than a meter per pixel, and we'll get that at many regions of Europa. And so the reason instrument provides narrow ground tracks of radar. Again, those can probe potentially all the way through the ice, and in some places they'll have cross tracks. They'll have coverage in multiple times of Europa in different places, different parts of Europa's orbit. That might allow us to also see the flexing of Europa's ice due to the tides. So the advantage of doing this, as opposed to orbiting Europa, is that it allows us to look at Europa at multiple distance scales. It allows us to conduct a whole bunch of flybys over a pretty reasonable period of time of 3.5 years. And most importantly, it minimizes the time spent in the very high radiation environment of Europa, which is a driving factor for the longevity of the mission. Because as I mentioned, this unique high radiation environment, although of interest for generating oxidants, is potentially deadly to spacecraft instruments. I haven't really emphasized this so far, but another aspect of this is that the mission plan involves conducting basically the same science investigation with each flyby. And so in contrast with Cassini, and in some ways with rovers on Mars, there doesn't need to be a lot of interaction and choosing of what to do with the instruments. Instead, all of the instruments will be on for each flyby. And so that's enabled by the fact that all of the imaging instruments on the spacecraft are pointing in the same direction. So as we fly by Europa, they can all be on. They're co-bore sighted, so they're all looking in the same direction, with just a little bit of gimbaling to minimize smearing for some of the instruments. And similarly, the in situ instruments, mass specs and SUDA, are pointing in the RAM direction of the spacecraft. So this is the direction the spacecraft will be traveling as it images Europa. And here are the magnetometer and the plasma instruments. Here's the high gain antenna that will radio information back to Earth, including during the Europa Clipper flybys. There are some ancillary antennas that allow pointing to the Earth, even for geometries where this antenna can't point to the Earth. And it's important to note also that the spacecraft is solar powered, so it's not using radioactive materials. And a key challenge for implementing such a mission then is to integrate the ice penetrating radar antenna directly onto to the solar panels, which effectively makes the solar panels a part of the radar instrument. So to zoom out then and show you the spacecraft in broader view, you can see we've gone through different designs of these high frequency antennas. In fact, the most recent design looks similar to these large wire antennas, just a smaller wire antenna. This gives you some more details of the spacecraft itself, but it also shows you the trajectory. It's kind of like a spirograph. It's a resonant orbit of Jupiter that flies by Europa every 14 days. So this is similar to the resonant flybys of Juno by Jupiter. So these elliptical orbits keep the spacecraft far out of the radiation environment. So we swoop through in a Keplerian orbit with a quick flyby of Europa, and then spend the majority of the time outside of the main radiation of Jupiter. So I'll end this presentation by showing you a single flyby of Europa in an animation, and we'll just walk through that. So here you see the instruments of the spacecraft. So and I pointed IceMag is now ECM, the Europa Clipper Magnetometer. Up here, you see the altitude above Europa and the relative speed to Europa. You can see some information about the activities. There's a timestamp up here. So I'll push play and we'll see how that works. So this is nominally 2028, April 9th. So just about 7 years from now. So you can see Jupiter there in the distance. You can see the spacecraft already has Europa in its sights. You can see we're doing some global scans with the UV instrument. The magnetometer and plasma instruments are always on. So they're getting some sense of the environment far from Europa. And as we get closer to Europa, so now within 100,000 kilometers, speeding up as we fall toward Europa, we do some thermal imaging of Europa in the global sense. You'll see the other cameras start to come on. You see we're getting some wide angle camera imaging. We'll do some scans of Europa with the UV and thermal, some more UV thermal, some more imaging. And as we get really close to Europa, below 10,000 kilometers, you'll see reasons start to come on to begin to build up that radar swath through Europa. Sorry, it's within 1,000 kilometers, I should have said. And so this is the main part of the flyby. And they're getting the most high resolution data for that part of Europa. We'll do the same thing as we're moving away from Europa. And we'll do that 40 times or so over a period of about 3.5 years. So yeah, we're actively discussing, refining these plans, and excited about now building our spacecraft. I believe if you poke around on the europa.nasa.gov, you should begin to see pictures of the spacecraft coming together. So with that, I'd be happy to discuss, take questions, etc.
Great. Thanks a lot, Steve. It was a great lecture. And there are some questions, actually. I will start with the first one. So the first one is by Sun Shuke, asking, different initial chondrite seems to create different mineral combinations. So how can we constrain the initial chondrite type?
Yeah, this is a complex problem that's partly addressed by modeling. So you're referring to this figure that I shared, and I think this is a really key problem here. It's a non-unique. So the way this manifests presently in terms of the ocean composition and the thermal state of Europa is going to be there are going to be non-unique answers to how this occurred. So part of the answer will be through modeling. Through inference based on things like the ALMA observations of planetary systems forming around other stars, where we have a chance of seeing how these dynamics play out in other worlds. Part of it will be through continued investigation of meteorite compositions to get clues to the possible composition of materials, but also we'll have clues from Europa Clipper measurements, namely. The hope is that we'll be able to get, for example, D/8, the deuterium to hydrogen ratios from materials that are from Europa's ice. We'll have to do some piecing together to figure out which of those represent pristine materials and not altered materials from Europa's ice. any clues we can get to Europa's ocean composition can tell us, will allow us to eliminate different potential models. So here's another figure from that recently submitted paper, and this is showing the solubility of minerals and gases for one of those. So these are the three models that I showed you: the CI, the CM, and that mixed model. I believe this is for the CM model, the mineral compositions. So you see the equilibrium minerals here, the seafloor, and also the dissolved ions in the ocean. And interestingly, in this work, we found that the solubility of some of these ions is actually variable with depth over the relatively great depth of Europa's ocean. And also the pH is depth dependent and is greatly different for these different models. And so this isn't meant to be a definitive model. This is an example, and we envision conducting thousands of such models. And so to get sort of a statistical feel of the ways that Europa might vary, and that will allow us to then to have, again, a framework to compare with observations, mainly about the composition of Europa, but also about the interior state, the density of the core, how big the rocky core is, and things like constraints on the ocean pH might also give us a sense of the amount of iron, the ratio of iron to magnesium in the interior, the iron to sulfur ratio, different things that then factor into understanding the global composition of Europa. So we're not going to know exactly what Europa formed from, just like we don't know exactly what Earth formed from, but we'll be able to have a working model that informs us to Europa's evolution through time.
Great, thanks a lot. So I think you already answered Duncan's questions about the mechanism, how surface sulfate minerals could be transported.
Yeah, I'll just add to my what I said earlier about sounding through the ice, by just emphasizing, there's this work on, porous flow through the ice. There's been some more recent work in 2014. We have another paper in submission about this. So we're keenly interested in the rates of oxidant delivery. But ultimately, Europa Clipper will be able to sound through the ice to see if these things are happening. And similarly, the JUICE mission also has a radar instrument, in fact, developed by a very similar radar team. Some of the same people are building that radar instrument. So we have complementary investigations that will investigate Europa and also Ganymede.
Yeah, speaking of Ganymede, Licia is asking, how plausible is extraterrestrial life in ocean worlds which have no water-rock interaction?
Yeah, this is a question that's close to my heart, because just as I assert that I don't think the idea of no water-rock interaction at Europa is reasonable because of the possibility of serpentinization. I don't think the possibility of no water-rock interaction at Ganymede is necessarily reasonable either. So that for those who aren't familiar, in these larger worlds, the pressures are so high that although there's evidence for liquid water oceans, the constraints on the depth of the hydrosphere are such that the pressure at the base of the ocean would be conducive to generating dense ice phases that would sink to the ocean. So the thought has been, we should go to Europa because Ganymede is not going to have any kind of melting at the seafloor, that is at the rock interface. However, modeling of the heat transport through those high pressure ice layers has inferred that the only way you can get heat to efficiently transfer through the ice layers, namely the radiogenic heat in the interior of Ganymede, is to have some amount of melt generated at that rock ice interface. So you're going to have melt generated there, and in fact, that melt, when it forms, is going to be buoyant, most likely, because if it's not very salty, it will be less dense than the high pressure ice, and so that will actually add to the circulation in the ice. And so you might, in fact, have hydrothermal systems in high pressure ice, in addition to some extent of water-rock interaction. So yeah, we're interested in what kind of water-rock interaction might occur in those worlds.
Great. So Adriana is asking, she seems to be a biology student and she wants to dive into the world of geophysics. So do you have any reference work, textbooks or publications you would recommend?
Yeah. Admire the bravery of wanting to dive into geophysics. It's actually, I think geophysics is pretty fun. It's applying in some cases some pretty basic physics to coming up with profound insights into geological problems that, the same insights that are applied to planets are also applied to Earth. And a book that's taught both to Earth geophysicists and to geophysicists studying planetary science is the book by Turcotte and Schubert. That's one that I learned from. I enjoyed that quite a lot. There are some other introductory books that are nice, but I like Turcotte and Schubert. I think it's a good balance of mathematical rigor and easy to read. And there have been some recent editions of that book. If you want some information that's very directly related to this talk, our 2018 paper, paper that I led, Vance et al. From 2018. I'm looking for a slide that has that reference, but we had a paper in 2018 that described the development of these kinds of wedge models using gravity data. And so some of the references therein also provide some, if you just want to get into the literature on this topic. And I'm happy to answer questions if you want to email me.
Great. So there's another question by Dana Camilla asking, how would the Europa's interior model change if the nucleus or its composition were different from what it's believed to have today?
So that is, if there were more or less of a core, is that sort of the idea?
I guess it's more about the composition. So if it's a little bit different than we expect it to be today.
Yeah, well, so I mean, in general, the investigation of ocean worlds is exciting because it gives us an alternate compositional scenario from what we find on Earth, potentially. I just want to emphasize we don't know a whole lot about what's exactly in Europa, and so our goal is to play with a lot of different models and to think about how they might influence habitability, and to I think answer the question in terms of how much variation we might get. I'll just refer back to this slide that I showed a second ago from this paper, in which we point out that things like the ocean pH might be quite different. I'll also emphasize that this pH, lower than 5 in all cases, is much more acidic than in this other model that I showed here from Zolotov, where the pH is at a minimum, 6.5 or above. So that's the range of our understanding of Europa.
Thanks a lot. So Shunsuke is asking, would it be possible to get the composition of the salty ocean from the magnetic induction data?
Yeah, that's a question close to my heart, and I have a whole other talk about that, which I considered giving today. So we had a very recent paper just out in JGR in which we constructed a bunch of models of Europa. We noted that the temperature varies quite a lot because the melting temperature of the ice is different. And what that means is that the conductivity is going to be different as well. So these are seawater magnesium sulfate models. And so we looked at, and you have to apologize for this complicated figure. What this is showing is the thickness of the ocean and the conductivity of the ocean, which are mainly what you get from the magnetic induction measurement. And this is just looking over a parameter space of those things from, a 200-kilometer thick ocean to a 1-kilometer thick ocean. And then, the models that we actually constructed are in a pretty narrow space. And you can look at then what is the corresponding predicted magnetic induction from Jupiter's rotating field, the so-called synodic, and then also from Europa's eccentric orbit. And you can ask whether you get unique signatures that help you distinguish between these different models. And so we determined that if you arrive at Jupiter at different times, you'll see our different models will have much different magnetic induction signals. And this is a lot of material that I don't have a lot of time to go into, but what I want to emphasize is that we expect Europa Clipper and JUICE should be able to sense signals that are stronger than 1 nanotesla. And so the differences between our models are in many cases larger than 1 nanotesla. And so, but this kind of work is the beginning of just as I mentioned, looking at a broad parameter space of likely models and asking how well you might be able to detect those different models.
Great. We have further questions. So there's Grish asking if you could elaborate on the potential role of Europa when thinking about panspermia.
Yeah, well, so I mentioned a possible independent of origin of life on Europa. So whereas there's some discussion about, well, maybe we're all Martians because because conditions that might have been amenable to the origin of life as hypothesized here, and also alternate hypothesis for the origin of life, those conditions might have occurred first on Mars. And because impacts around the time that Mars formed and Earth formed would have brought materials to Earth from Mars pretty regularly, perhaps we are Martians. So by contrast, it's harder to get materials from Mars or Earth to Europa. And so maybe, an independent life, origin of life there could have happened. So I think ocean worlds are an interesting laboratory in that sense. Now, as for panspermia in the sense of did life come from outside the solar system, it would indeed be very interesting if we found DNA-based life on Europa that uses the same base pairs that we use. That might be interpreted as meaning either that there was communication of material from Mars or Earth to Europa, or by material from Europa to here, or that we're all from some external origin. But yeah, I do think the search to understand, the quest to understand life in our solar system, it does have some bearing on this idea of panspermia.
Yeah, thanks a lot. There's another question by Krish asking, is there any chance that we find out if there are potential tides caused by the other Galilean moons for the subsurface ocean?
So the question is, would tides in other moons create oceans? Well, so there's evidence for, in fact, yeah, I should have emphasized this earlier. The same magnetic evidence for an ocean in Europa was also found in Callisto. So even though Callisto is heavily pockmarked, it also showed evidence for an ocean. And in fact, prior to the Voyager arrival at the system, it was thought that Ganymede and Callisto might have been the more likely cases to have oceans, and Europa would be the most boring. So that's kind of an interesting footnote. The only reason that we didn't see induced signature at Ganymede is that Ganymede has its own internal magnetic field. So it's the only moon that has its own magnetic field. But what that means is that it has a dynamo, like a molten iron dynamo in its core. And so what that means is that its interior is probably very warm, and so almost certainly there's an ocean there.
Great, thanks a lot. Anisha is asking, if we do find evidence of hotspots on Europa, what more information would it give about the geology of Europa, and would it suggest anything about the existence of extreme life?
So there are two kinds of hotspots that we might think of. I added this figure from that paper that I mentioned that just came out, showing the likely or the predicted amount of melting 2.1 billion years ago on Europa, showing that there would have been melt generated throughout Europa in a three-dimensional sense. This is like a globe of a global map of Europa, and showing that in the present day that melting would have been confined to the poles, or it might be today confined to the poles. So if we find that kind of thing, it might suggest that there could be life in hydrothermal systems. Again, I'm excited about the prospect that if these are present, they might communicate to the ice directly above them, and we might be able to sample or observe the effects. So the other type of hotspot might be the type of melting near the surface, the chaos features. And if we see active chaos features, there's what's exciting about those in part is that there's a higher likelihood that the surface materials that we sample with our mass spectrometer and our dust instrument might contain clues to the composition and even the presence of organics in those briny regions. Now, melt within the interior, within the ice rather, would be sustained by having a high concentration of salts. And so we have to ask, what types of organisms on Earth can survive in such environments. And indeed, those are very extreme. I suppose the biologists in the room here know quite a lot about this. It's only certain organisms that can live in the very low water activity conditions of highly briny solutions. And so, yeah, so an interesting field of research for the coming years will be to think about the types of extremely high salt environments in Europa's ice that might exist.
Thanks. Hermes would like to know, or he's curious about the Europa lander mission. Can you elaborate about that a little bit?
Sure, yeah. So if you go to europa.nasa.gov, I believe there's some resources about the Europa lander concept. So NASA has been studying a follow-on or perhaps potentially even contemporaneous lander mission. So the Europa lander concept is pretty far along in its development. So there's a plausible concept, partly using some of the technology that was recently demonstrated for the Perseverance rover of terrain relative navigation that was helpful in shrinking the landing site, the landing ellipse. And just this week there was a Europa in situ workshop pertaining to possible instrumentation for such a lander. I'm involved in a group that's thinking about seismic measurements. We're interested in the seismology of Europa as a way of providing further information about the ocean and the ice.
Connected to that, are there plans to drill through Europa's ice at some point, or is the risk of contamination of Europa's ocean too high?
These are such great questions. So there, in even more recent years, there have been next generation studies to think about drilling through the ice. The idea of drilling through the ice has been of interest to people like Bill Stone of Stone Aerospace for quite some time. So this is related to Antarctic drilling campaigns that try to drill through the ice. So there in Antarctica, you have the benefit of being able to bring diesel engines and lots of equipment with you. At Europa, you would almost certainly need to have some kind of high energy source like a nuclear power station. But the idea of drilling through the ice is really intriguing. I agree that the planetary protection component is a concern. And that's one reason why we might want to consider waiting to drill through the ice in order to avoid contaminating the ocean. The discussion of your risk threshold for contamination is a difficult one, or it's a fun one to have, I suppose. And I think for different people, the thinking will be different on that. But I think as a civilization, we have to think about what we want to do and how important it is to be able to have a pristine Europa in which to study.
Great. So I think you already answered Dipanu's question, but I will repeat it. Are the geophysical conditions more feasible for existence of life in Europa compared to Phobos or Titan?
Right. Well, so this is a discussion. So Phobos, I'm not. So that's a moon of Mars. I'm not sure about the case for life on Phobos. So I'll just talk to Titan. So they're just very different worlds. Titan is also an ocean world, a liquid water ocean, and then also has this interesting hydrocarbon environment at the surface, which looks really intriguingly Earth-like, given that it's sculpted by rain and winds and such. But temperatures are 100 Kelvin, and the fluids are hydrocarbons, methane and ethane rather than water. So life as we know it, doesn't live in such in these non-polar solvents. So people like to think about how life might exist in those conditions, but it's kind of an extreme from my point of view. And the possibility of life in the water ocean of Titan is also intriguing to me. I'm part of a team that's looking into that. But I think the available energy is going to be less than that at Europa, most likely.
Okay, thanks. So Hector is asking, as the ocean chemistry of Europe is very dependent on the bulge or the inner core of Europa, can you compare it to either like igneous rocks like on Earth, Mars, or maybe more like their moons or meteoroids or asteroids and comets?
Yeah, well, so I think it's important to think about, well, how might Europa differ from Mars and Earth? So I mentioned the iron to magnesium ratio, the iron sulfur ratio. These are things that are set by the bulk composition, and so this is why the meteorites are important. It's not so much how will Europa, like, will Europa morphologically look like meteorites having the same grain size and such. It's more, what are the elemental abundances in those meteorites, because the vision for how Europa formed involves those materials accreting, that is, falling into a gravitational well of the forming Europa and clumping together by gravity. And at a certain point, when Europa is tens to hundreds of kilometers large, and as radioactive materials, especially in the early days when there was short-lived materials like iron 60 and aluminum 26, you would expect that those materials would heat up to a high temperature and would then separate out their materials. And so the fact that Europa has this great density gradient suggests that that happened pretty efficiently. And so in that sense, because Europa has a metallic core, we can think that in the general sense, it might be similar to Mars and Earth. And so the composition of the minerals is going to differ more in terms of the influence of pressure and temperature on mineralogy. So no, I think it's a great question, and there are a lot more details to that answer. But I think it's important to think of Europa as more like Mars and Earth than like comets and asteroids.
Thanks a lot. So one last question. If you would have a wish free, is there an instrument not planned for the Europa Clipper mission which you would love to have on board though?
That's a question that I will plan to have a good answer for in the future. As I mentioned, I'm excited about doing seismology on Europa, and I'm keenly interested in doing seismology on larger worlds, mainly because there are these questions about the presence of melt under the ice, and in some sense, a seismometer is the best instrument to try to determine the exact thicknesses of the different high pressure ice layers. So in Ganymede, we have not just ice 6, but potentially ice 3 and 5 as well. Yeah, so seismometers are the ones that I'm thinking about mostly. Great.
So this was the last question. So thanks again, Steve. It was a great talk, and I think it was a great end of this lecture series. We had a great week. And I would like to thank you, Steve, all the other speakers from this week, and of course, all the attendees, because without attendees, this school wouldn't make any sense. And thank you. I think it was a great success. And maybe, Barbara, you want to close this?
Yeah, just want to say thank you to everyone, especially to our last speaker, because for us it's Friday evening. So we still had a big number for you, Stephen. So you can be very happy about. And thank you. Your talk was very interesting. Also to me, that I'm not completely interested in icy moon, but I learned a lot. Thank you very much. Thank you to Ruth to support for 5 days the school, and thank you to all the attendees. We will wait for you for the EANA 21 annual virtual conference in spring. If you're interested in, just Google EANA Astrobiology European Network, and you will find all the information. Thank you very much to all, and have a nice weekend. Bye.
All right. Thanks so much for the invitation. Take care, everyone.